Okay, so here we are. This is the fifth lecture. I did remember to record, so hopefully I'll get that posted later. I graded the quizzes. If you did sixes or below, maybe you should come and see me in my office just to go over some stuff and make sure you're on track for, where we are in the course at this point and what you know and what you don't know. I want to tell you that I am in my office. I think my office hours are like Thursday afternoon and after class either day and Friday morning, but nobody comes on Friday. So I think I'm going to have my office hours. I'm going to be there Tuesday and Thursday. Now, I know some of you have lab from 12 to 3, but I'm going to stay after 3, right? So I'll be there like in my office after class. And then I'll stay until at least 4, okay? And the same thing here. And then Wednesday, I know some people come around on Wednesday. I'll try to be there after maybe let's say 2 to 3 for a definite. Okay. But I'm really going to be there later than that. That's kind of like the way I work. Okay. And now, is there someone here that can't make any of these office hours? Raise your hand. And when would you like to have an office hour? How about before class? Because I'm here at 9:30 every day. Really a quarter after, but today I got stuck behind a semi truck bringing some construction equipment, so that didn't happen. So also, in this room before class is good as well. Okay, so like after 9:30. All right, so that's what my new office hours are going to be. Tuesday, Thursday, from like 12 to, well, I mean, it's a lot of time to commit to. But all right, Wednesday 2 to 4. That's kind of when I'm here, and then before class. Okay. I may have to modify this if I decide to go swimming in the afternoon. I went over to the rec center yesterday, but for now, that's what it's going to be. So there's lots of times that you could find me. Some people did come by before the last quiz. Anyway, so I'm going to continue from where I was. So I was talking about mass spectroscopy, which is very relevant to your lab today. So you might want to listen up because you're going to be a little lost if you don't kind of know a little bit about what's going on there. And what I said last time was that you could put a mixture of stuff into this GC this gas chromatograph mass spectrometer. And I believe I already explained how the gas chromatograph separates the mixture into its individual components. And then each component, which is a compound or an element, goes into the mass spec at a separate time. So all the separate components go in at their own time. And so what happens in the mass spec is that it separates based on mass. So what you end up with is a plot of, so remember what's happening is you have this weird thing. You have these, let's say if you have, I gave the example of magnesium. Suppose magnesium goes into the mass spec. At some point, the magnesium atoms are bombarded with electrons. Okay, and what happens is this electron causes, what it does is it kind of knocks another electron off, knocks an electron off of magnesium. When you take an electron away from an atom, you have a positively charged ion, which we call a cation. So you started with this electron that was thrown into the magnesium, and it knocked off another electron, and that second electron is over there with the 2 electrons. So you have the original one, and then you have the one that gets knocked off, and then you have this positive ion. Anybody know what we call a positive ion? It's a cation. Yeah. Okay. And if magnesium goes into the mass spec, Okay, what the mass spec does. So now you have these magnesium pluses. I'm going to just put them in a different color because now they're magnesium ions. These are the Mg plus ions. They get bent according to their mass. They get bent more if they're lighter. So the lighter atoms end up here. They're bent more. And the heavier ones, so in this part, they're like not bending as acutely. Heavier atoms are bent less by the magnetic field. So it's a magnet that bends these guys. You put an ion or a charged particle in a magnetic field and it bends its path. Now you might think, oh, you just have magnesium. That's only one type of particle. Is that true? How many types of particles are there? What is that according to? It depends on the number of isotopes. And in a sample of magnesium, you have magnesium 24, you have magnesium 25, and you have magnesium 26. And so when you're talking about, you're going to end up with 3 spots here. There'll actually be 3 things here. These magnesiums will go in they'll end up in 3 different places. So in your detector here at the end, you'll have a spot, which represents magnesium 24, and then spots that represent where the other particles hit in the detector. And so this axis becomes mass because, you have 24, 25, 26. And now we can make a graph of the intensity, which is proportional to how dark that spot is, how many particles hit at that spot. Yeah.
So electron.
No. That's not what happens. The electron knocks off an electron from magnesium. This magnesium loses an electron, then these 2 electrons are these 2 electrons here. No, the electrons are not detected. The only thing that this detector detects, and that's a good point. Well, basically, I've left out some of the apparatus here. There's some plates here that accelerate positively charged particles, but don't accelerate the negative ones. So the negative ones fall out, they go somewhere else. It's only positive ions. Only positive ions are detected in the mass spec. Okay. And then I was saying that how the heaviness, the darkness of the spot tells you how many particles hit, and we call that intensity. So you'll actually have something that looks kind of like this. At 24, you'll have a very high intensity because you had the darkest spot. At 25 and 26, you'll have much smaller intensity peaks. And this is called the mass spectrum. Okay. So what we did last time was I told you what the intensity of the peaks were. And the other thing the mass spec gives you is the precise mass. Notice how many decimal places this goes to. Maybe not the instrument that we have in our department, which, by the way, now is in storage somewhere because we're having this building move. But a really good instrument can measure this, not just 24 here, be 23.985042. We could measure it to many places. And what I showed you last time was how to get the fraction in decimal form or in percent form, how to get the natural abundance of each of these. So what we want to do is we did last time is we summed up the intensity of all of the peaks and then divided the intensity of each peak by that sum to get the percent natural abundance. And that's what we did. So you could see here, this is the intensity of the 24 peak divided by the total. Remember, we added them up and we got 555, 555 when you add this up. So we divided each of the individual intensities by that, converted it to a percent. So now we have the percent natural abundance of each of these isotopes. And now I can figure out the mass of magnesium. I'm going to do a weighted average mass. And to do that, you take the natural abundance of each one, 78.9900. Well, I convert that to a decimal. So it would be 0.789900 times the mass, which is over here, of the first isotope, the one at 24. And that's 23.985042. And I add that to this converted to a decimal, which is very nice and easy, all zeros, times that isotope's mass. And then the third one, 0.11010 times 25.982593. And when you do that, you get 24.3050. And if you look at the periodic table under magnesium, it says 24.305 or 24.31. And that is how that number is obtained. So there's a lot behind that number on the periodic table. So I want to tell you a little more about the mass spec so that you can do the other stuff in the lab today. So when you have a collision, so when you take something like we did here with the Mg, and it's bombarded with electrons, and all that happens is that you get a positive ion and an electron. We call that a soft collision. So a soft collision of, say, aluminum in the mass spec would give you an aluminum plus ion and 2 electrons. So in other words, an electron comes in, it hits this aluminum, and an electron pops off of this aluminum. Actually, this is the electron that hits it, and it pops off with an electron. And these 2 electrons are these 2 here, the original one plus the one that gets knocked off of the atom. So this is what we call a soft collision. For a single atom, there's nothing else that can happen. There's no fragmenting that's possible. But this can also happen with molecules. So what if a molecule goes into the mass spectrometer? Okay, so let's suppose we have C4H8O. Okay, so if it is bombarded with electrons in what we call a soft collision, all that happens, okay, is that this guy, which has a nice electron cloud around it, loses an electron. An electron gets knocked off the molecule. And we write that with just simply indicating that by a positive charge, because it has one less electron than it should. Where did that electron go? It's now combined with this one. So now we have 2 electrons. So this is what happens for a soft collision of a molecule. Now, this thing here, this is the original molecule with 1 less electron. Okay? Do electrons have anything to do with the mass of a molecule? I mean,
No.
Yeah, the mass of an electron is basically negligible compared to masses of protons and neutrons. So the mass of this guy is the same as the mass of this guy. So this positive ion will be detected. So the question is, where will a peak be seen? And remember when we did the magnesium, the x-axis is mass. So the question really should be is what mass? And to do that, remember when you figure out the mass of a molecule, so here there's 4 carbons, so that's 4, let's just do it to the nearest whole number. You would look up carbon on the periodic table, you'll see it has 12 underneath. So the mass is 12, there's 4 of them. That's 48. Then you would have 8 hydrogens. That's 8 times 1. That's 8. Then you would have 1 oxygen. That's 1 times 16, or 16. And if you add this up, it comes to 72. So in your mass spectrum, where you have mass here, you'll see a peak at 72. Okay, there will be other peaks, but you will definitely see a peak at 72, because what you're seeing is what happens when this positive ion hits the detector. It only detects positive ions, but the mass of C4H8O plus is precisely the same as C4H8O. And why is that again? Because they only differ in mass by an electron, and electron masses are negligible. Only it detects the positive ions. Okay, so I'm going to tell you that this peak, which is the original ion, the original molecule, I'm sorry, with 1 less electron, leads to something we call it the molecular ion. Molecular ion. In other words, the original molecule. That's the molecule we're talking about. This is called the molecular ion peak. Now, it's basically to the right of the spectrum, right? Because you can't get more mass than that. That's the mass of the molecule. It can't grow in mass. But there could be fragments that have smaller mass, a piece of this molecule. So what can happen, and I talk about this here, okay? What I've been talking about is a soft collision, where you only end up with the positive ion from the original thing you started with. And we did this one already. That was aluminum. But what if you had a molecule like SO2 and you put it in the mass spec? So what's going to happen is so the electron comes in. So what am I going to write here? Plus 2. That's right. This is basically the same idea. And so what if we had C2H4O2? Well, same thing. You hit it with an electron. So what would I get here? O2 plus, taking 1 electron off. You're not taking an atom off. That's not what I'm talking about. These are soft collisions. Okay, but the thing is that there are other things that happen in the mass spec that what can happen is there can be something called a hard collision. And hard collisions fragment these molecules. So they break the molecule into fragments. Okay. And for example, let's suppose let's go back to C4H8O. Okay. A soft collision, if you recall, gave you this. So this was a soft collision, C4H8O plus 2 electrons, but a hard collision. So now you started with the same thing, but instead of just getting this molecular ion, instead of it just losing an electron, it breaks apart. And this is something that can happen, that you could get, okay, 1 of the carbons, 3 of the hydrogens, and the oxygen, and that has lost an electron. So you still have the 2 electrons, right? You had an electron came in, this electron came in, it knocked an electron off of that. So you got 2 electrons, but it also broke the thing apart. So my question is, this is a big question here. If this is 1 fragment, what does the other fragment have to be? So let's take a look at this, okay? It's going to have So remember, we have to conserve mass here. That means we have to conserve the number of atoms of each type. So we have 1 carbon here, but we had 4 carbons here. So how many carbons are we going to have in this fragment? C3. Okay, we have 3 hydrogens here, but we had 4 here. So H, well, 1, but you don't put a 1, you just leave it as H. And what about O? Wait a minute, what did I do here? Oh, yeah. Oh, sorry, I wrote this wrong. This is H8. Sorry. Yeah, so this is 3, this is 8, so this has to be 5. And that's it, C3H5. There's no O. The O is already in the other fragment. So that's the thing that's missing. See, the O is here. There's 1 O here and there's 1 O here. So we're done. So the other fragment must be C3H5. Okay, now this is the fragment that you would see in the mass spec. Why wouldn't you see this one? That's right. This is not a cation. It's not a positively charged ion, so it will not be seen. So it's not seen. But this one will be seen in the mass spec. And at what mass would it be seen? Okay, where would you see it? So you would say, okay, CH3O plus has 1 carbon. That's 12. If you look on the periodic table, 3 hydrogens, that's a mass of 1 on the periodic table, plus 1 times 16. So that's 12, that's 31. So on the mass spec, remember, you'll see a peak at 72. What do we call that peak? The name of it, we call it the molecular ion peak at 72, but we'll also see a peak at 31, which is from the CH3O plus. Okay. Now it could also break up this way. You can also have this possibility. Suppose that that's the positive ion that you get. Okay. You still have 2 electrons, right? And now when you fill in what's missing here, you see that you need 1 carbon to fill it, 3 hydrogens, and an oxygen. Okay, so this is the other fragment. Notice it's just the positive that I've switched. It's the same 2 fragments, but I said, okay, what if this forms and it's the positive ion? Then you could fill in what's missing here, right? 3 plus 1 from this one gives you 4. 3 plus 5 gives you 8. See, it's all just conservation of the number of atoms on each side. Yes.
So is the breaking apart, does it have a rhyme or reason? Is it?
Well, I guess, this molecule is being bombarded with electrons. A whole bunch of them are being bombarded with electrons. Some of them, the electron might not hit quite as dead on as another one, So it kind of matters how the hit happens. And so all these different fragments form, many different fragments form. But the beauty of mass spec is that when the molecule fragments, it's atoms that are close together that end up in these clusters of these particular fragment molecules or positive ions. And that is what allows chemists to figure out what was the structure of the molecule originally. So if we didn't have the fragmenting, all that we would get from this method would be what is the mass of the thing being analyzed. But the fragmenting allows for figuring out what is that molecule, was it this drug? Was it this, illegal substance? Was it, because Mass spec is used all over crime labs, all over the place. Not just crime labs, it's used in pharmaceuticals. It's used to figure out if you do a reaction, what the heck is in the soup at the end of the reaction, you know, and that's a big deal in chemistry. Yeah.
So, this is given.
Well, I mean, that's what we're doing in Chem 103 in an exercise.
Okay.
Yes. But that's not given. When you put something in the mass spec, you usually don't know what it is. That's why you put it in the mass spec. Yes, that's right.
But how will you find other?
Well,
nons?
You do it by summing up, you know, getting the total number. 3 plus 1 is 4, or just like we did. Yeah. All right, so that means since this is a positive ion, you would see this in the mass spec. And you would see it at 3 times 12 plus 5 times 1, right? The mass of carbon is 12, the mass of hydrogen is 1. So that would be 36, 41. So you would also see a peak here at 41. So you could see the masses of all these fragments, and you could sum it up and figure out what is the structure. Now you can't do that, but other people, you know, people who do this for a living can. So I just have this little exercise. I'm just going to do the first one. I'll take B and C as special problems that I'll collect next time, Tuesday. So what happens here? Okay, you knock off an electron. So you get 2 electrons here, C2H2 plus. So what would I have here? Don't forget the oxygen. That's right. All right, the pen's not, yeah, we go. So now we have 2 oxygens here, we have 2 here, we have none here. That adds up. This carbon is 1 carbon plus 2 carbons gives you 3 carbons. That adds up. We need, so this is 4 hydrogens plus 2 hydrogens is 6. So that adds up. And so, and then we have the 2 oxygens here. So that adds up. Okay, so these I'll collect at, next time. I'll give you a chance to do those for special problems because I do need to move on. Okay. All right, so now I'm going to start talking about sort of the next big thing in this chapter. So in mass spec, like I've just been talking about, we force electrons on, you know, we bombard the sample with electrons. It's not a very natural situation. It's kind of an exceptional situation. And by bombarding them with these electrons, we knock off electrons from everything that's in there, and we create a positively charged ions. But that's a really exceptional situation. So I'm going to say that normally an atom will either lose or gain an electron based on its properties. So my new topic here is really ions. And I'm going to talk about it with respect to the periodic table. So a lot of what I'm saying is just really going to be about the periodic table. So it's kind of an intro to the periodic table and to ions. So normally an atom will either lose or gain an electron based on its properties. And the properties will determine whether it gains or loses an electron. And what I mean by that is not something I can really tell you now because we haven't really learned about those properties yet, but we will later in the semester. So I just want to show you, if you look at the periodic table, so I'm kind of giving you the conclusion before I tell you more about it. If you look at the periodic table, you can see that on the right side of the periodic table, so let's take a look at this. First of all, let me talk a little bit about the periodic table. The rows. So the rows are called periods. So we say this is the first period. This would be the second period. Don't, sir, I'm going to erase this because I have other things to show you. The third period. So this is period 2, period 3. But I really want to show you the numbering system. There are 2 different numbering systems in the periodic table. So this periodic table is numbered from 1 to 18, all the way across. So we have the periods going across, but the columns are called groups, or sometimes they're called families. Okay. And you could number them this way, just 1 through 18. Another very common way to number them is to call this 1A, 2A. And then you continue with the A groups on this side. Notice that whenever there's if it's 13, it's 3A. If it's 14, it's 4A. 15, 5A. So it's kind of and we call the first 2 columns and these columns at the end here, those are the A groups. And then these guys here, we call the B groups. And I don't even care if you know how to number the B groups. That's not something we're going to concern ourselves with. But what you notice here when you look at the periodic table is that you have in the last column, these guys, these do not form ions. So what I have written here are the ions that would be formed from the atom in that box in the periodic table. So you could see here that these do not form ions. These are the noble gases, also called the inert gases. They're not as reactive as other gases. It used to be believed that they didn't react at all, but that's not believed. That's not true anymore. We know more about it now. You could see here that you have negatively charged ions that form from the atoms to the right of the periodic table. Anybody know what a negatively charged ion is called? Oh, no, a cation is plus. These are anions. Yeah. Negatively charged ions form from many atoms on the right of the periodic table, but not including that last group. And I would say that I would cross this out. Carbon does really not form stable ions. So there, I'm getting rid of that one. A lot of the ones that are left blank don't form ions, but that's not true. These guys in here do form ions. Just the ones on the right. Don't worry about it. I don't want to get into too much detail right now because we haven't really covered this stuff. But you'll notice here that that this part of the periodic table, so the left side and the middle, so those B groups plus the A groups on the left form positively charged ions. Okay, so you could see that the periodic table somehow organizes elements in terms of their properties, because you could take a look at the ions that form and see that you never have a positive ion forming from something way to the right on the periodic table. And you never have a negative ion forming from something that's on the left of the periodic table. So there is some organization that goes according to properties of the atoms in the spot. So I kind of want to spend a little time talking about the periodic table, and not very long, but a little, just to give you a little bit of an idea. So the periodic table is organized, the modern day periodic table is organized by atomic number. Remember, that's the Z value. That's the number of protons in the nucleus. But you have to realize that the first periodic table, which was published in 1869 by a guy named Dmitry Mendeleev, who, by the way, is from Siberia. So somebody from Siberia came up with the first periodic table, 1869. Does anybody remember when the Rutherford experiment was? I'm sure you don't. You don't need to. What it was what? Oh, way after. So the Rutherford experiment, and remember the Rutherford experiment was one where they figured out that there was a nucleus. They didn't even know there was a nucleus until then. The Rutherford experiment was, say, let's call it 1910. So back when Mendeleev put forward the first periodic table, he didn't even know there were protons. He didn't even know there were protons in a nucleus. So he couldn't organize the periodic table based on atomic number. What he knew was atomic mass. So in 1910, there's basically, in 1869, I mean, there was really no knowledge of atomic structure. No knowledge of nucleus that contains protons and neutrons, etc. None of that was known. And, you know, the Rutherford experiment that began to have people think about the atom as a planetary model didn't come about until many, many years later. So what Mendeleev did, he used atomic mass because that's what he had to organize the first periodic table. And honestly, what he did was he made note cards. So he had a card for each element, okay? And he wrote down the name of the element, you know, let's say aluminum, and then maybe he wrote shiny, and he put its mass. I don't know offhand. I think it's a mass of aluminum. Let's call it 27. Okay, so we had, you know, for hydrogen, he had gas and some other properties, and then he had 1 for its mass. Okay, and he had these note cards, and he arranged them by mass. So, you know, he put them in rows and columns, and he noticed that if he had a row of a certain length, that all the ones that were lined up above and below each other, all the columns had elements that had similar properties. I'm just like amazed by that. I think that's really cool, you know. He noticed that if he did this in a certain way, that the properties, I'd say similar properties, could line up in columns. Okay, and actually that's why this thing is called the periodic table, because the properties kept repeating. It's like a period, you know, period's like a wave, goes up and down, it has a period. And so it's like the properties that kept coming back. And so so there was a pattern in the properties that repeated, hence the name periodic. So that's how the periodic table kind of got its name. Okay, now he was so convinced of this repeating pattern that he refused to put an element under the one above it unless it was similar to it. He insisted in similarity in these columns. So let me show you something that he did. So here's I gave you this picture. There's an old periodic chart. And what Mendeleev did was, for example, he had titanium here, titanium 48. So that's the next element that they had. So you might have figured it should go under aluminum because it was the next one. So he skipped the spot below aluminum. Why do you think he did that? He did that because titanium is not similar to aluminum, but it is similar to silicon. So he put it under silicon, okay? He skipped the spot below aluminum, and the reason was because titanium is similar to silicon, not to aluminum. Yeah. So he predicted there would be an element there. Okay, and it wasn't perfect. If you look it up, it's nowhere near what it actually is, but that's because of the transition metals, but at least he knew to leave a space. I'm not saying it was all worked out by then. Okay, another thing he did, notice here, these are masses now. These are not atomic numbers. These are masses because he arranged them by mass. He took iodine and he put it underneath bromine because iodine is similar to bromine. Okay, so another thing he did was he put iodine below bromine because of this similarity. Because they were similar. But what happened when he did that? What happened is the order of increasing mass wasn't adhered to. So he thought that that similar property thing was more important than keeping mass increasing, because you notice that 128 is bigger than 127, right? So he did that because it was similar, and he did this even though it disturbed the order of increasing mass. Now, what happened, of course, was when protons were discovered and we knew what an atomic number was, when then you started organizing the periodic table in terms of atomic number. And the reason why this mass flips is because there's heavy, is like that Te has more neutrons, doesn't have more protons. So when you put it in terms of atomic mass, this order stays the same, but the atomic, when you put it in terms of atomic number, the atomic number does increase. So when they figured to put it in terms of atomic number, the problem went away. Okay, so the later it was organized in terms of atomic number, and these discrepancies disappeared. Well, at least this one did. Okay, so what else can I tell you about the periodic table? So here's the periodic table. First of all, I've already pointed out these A groups. In the middle, we just call them the B groups, the transition elements. These are called the transition elements. We have another numbering system that I said, 1, 2, which you just go all the way across, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So this, like I said, 2 different numbering systems. What you need to, well, these first 2 columns, these first 2 groups, and all the groups on this side, these are called main group elements. So that's in red. Okay. And then the other ones are the transition elements. The main group elements are sometimes called the representative elements. I will never ask you that. I will never ask you what are these groups called, because I don't care. Sorry? Well, all of this periodic table all has to do with that, which we get to like later on in the semester. Okay. Now, what is done with the periodic table is these, oh, by the way, these 2 columns down here, the lanthanides and the actinides, we don't do anything with these elements. This is actually a continuation. Notice that there's this kind of, it's telling you to go. So basically from this element, it goes down here, 57, this is 58. If you put the transition, the lanthanides and actinides in a periodic table and lined everything up according to properties, this is what the periodic table would look like. Okay, and we don't have pieces of paper that are long and skinny like this. So these 2 are put on the bottom. Okay. And honestly, we don't do anything with these, so we don't really care about them in this class. So in this class, we really deal with this part of the periodic table. Okay, we have the A groups on either side and the transition elements in the middle. I call them the sunken living room of the periodic table, but you know, it was very fashionable, maybe in the 60s and 70s, to walk down a few steps into the sunken living room of a suburban house, you know, whatever. Okay, so here's another slide I gave you, and this doesn't quite look right on the slides. It includes this column 12 here, which is really shouldn't be, but these are the main group elements. And you don't have to know these names, but you really should know that this last, by the way, this is 1A, 2A, 3A to 8A. So that's kind of a good thing to know. Anyway, 8A is the noble gases. That's a name you really should know. 7A is called the halogens. That's like fluorine, chlorine, bromine, etc. These I don't even know how to pronounce these, pnictogens and chalcogens. You don't have to know those names. The alkali metals is a good name to know. Why did it do that? Okay. Okay. Where am I? Oh, yeah. Right. Oh, I guess it took away the names that I wrote, but I would know these names. And that's really it. Okay. So before we go back to talking about ions, I want to talk about one more very big organizational item that about the periodic table. Okay. And by the way, I cut off the lanthanides and the actinides because I don't really care about them. And that is metals versus non-metals. Now, if you took chemistry in high school, I'm sure you learned about this. These guys, including aluminum there. Oh, it took away. This whole side of the periodic table, except for hydrogen. These are metals. And then we have this guy, hydrogen, plus these guys are non-metals. Okay, and then we have these zigzag elements in between. Does anybody know what we call these? Metalloids. Okay, so let me talk a little bit about metals versus non-metals. They have different properties. First of all, metals are shiny. Okay, non-metals, well, many of them are colorless gases, but if they are solids, so let me write if solids, they are dull. They are not shiny as a rule. Metals, you know, they make radiators out of metals. They make wires out of metals. Metals conduct heat and electricity. They make pots and pans out of metals. Non-metals, by and large, do not conduct either. So there's a distinct difference between these two ends of the periodic table. Metals are malleable. Would anybody know what malleable means? Sorry? Yeah, oh yeah, bendable. They can be pounded into sheets. So you could have aluminum foil or tin foil or even lead foil. You really don't want to have lead foil, but malleable means you can pound into sheets. and you could bend. They are also ductile. Ductility means you can pull it into wires, and nonmetals are brittle. You cannot bend them or stretch them into wires. For metals, most of them are solids at room temperature. There's one liquid, mercury. Non-metals, there are many gases. There are no metals that are gases, many gases. There are also many solids, and there is one liquid. Okay, so metals are basically solids at room temperature. This is at room temperature. Okay, and also among the metals, you will find no diatomics. So Bro-Finch, if you remember, all of those Br2, O2, F2, etc. These are all nonmetals. Okay, so there's some very distinct differences in properties. And then we have the metalloids, which are very, very interesting. And they occupy that kind of intermediate region between the metals and the nonmetals on the periodic table. I'm just going to say they're sort of inside the zigzag in the periodic table. Boron, silicon, germanium, etc. Okay, now what about these? What are their properties like? Well, they kind of have some in-between properties. So whereas metals are conductors and nonmetals are semiconductors, sorry, I said that wrong. Metals are conductors, nonmetals are non-conductors. Many metalloids are semiconductors, okay? Which means they're sort of in between in the conductivity. And of course, that makes them very useful for technology purposes. Another great thing, a good example is silicon. Silicon is a metalloid, and it's shiny like a metal, but it's brittle like a nonmetal. So they are an interesting bunch. So chemistry does have middle ground, which makes it interesting as far as I'm concerned. Okay, so that's my little spiel about the periodic table. I'm going to get back to it very soon when we start to talk about ions. But before I talk about ions, I want to tell you about the two different types of compounds that we study in this class. And that is ionic and molecular compounds. So there are two kinds of compounds that we talk about in Chem 103. Okay. Molecular compounds consist of molecules, right? These consist of molecules of two or more atoms that are bonded together where the electrons are shared between those atoms. Okay, so, and these bonds where electrons are shared, we call these, anybody know what we call them? Covalent bonds. So for example, in water, these things here, these guys here, these are covalent bonds. Okay, they're shared between the O and the H. What about ionic? So ionic compounds are different. They consist of charges. So they consist of positive and negatively charged ions. Positive is the cation, negative is an anion. So every ionic compound has cations and anions. these are held together by the forces of attraction of plus to minus, which we call Coulombic forces, held together by the attraction of like charges. Sorry, unlike charges. Oh, I didn't have enough coffee this morning. Of unlike charges, which are called Coulombic forces. Okay. Another thing is that these, well, first of all, these attractions are called ionic bonds. So an ionic bond is simply the Coulombic force of attraction between positive and negative ions in an ionic compound. Okay. What I was going to say, okay, before I said that, is that when you have an ionic compound, you have a continuous array of positive and negative charges. You cannot identify a, quote, molecule. In a molecular compound, you can identify an actual molecule, a separate cluster of atoms with bonds between them. One here, one here, one here, one here, one here, one here. In an ionic compound, you have a continuous array of positive and negative charges, and you cannot discern a molecule. I'm going to show you an example. So here's sodium chloride, our favorite ionic compound. Okay. All right. The chloride is the big green things, chlorides. These smaller ones are sodiums, Na plus. And this is what you have in a sodium chloride crystal. Na plus, Cl minus, Na plus, Cl minus. Every sodium ion is surrounded by chloride ions. Every chloride ion is surrounded by sodium ions. And this is a continuous array. There are no molecules. There is no NaCl molecule. It just doesn't exist. So why is this called NaCl, and what do we refer to that as? NaCl is just the simplest unit of this compound. Okay, it's like the reduced. You wouldn't say Na3Cl3, you would reduce it to NaCl. So, but it is not a molecule. There is no NaCl molecule. So we call this a formula unit. Okay, it's the simplest unit of an ionic compound. Okay, now sodium is a metal. You look on the periodic table. Here's a periodic table down here. Sodium, I circled it here on the left in red. It's a metal. Chloride is a non-metal. So let's go back up here. So we have Na plus. Oh, let's just start with sodium as a metal. So it's on the left-hand side. Metals tend to lose electrons, and they form positively charged ions, which we call cations. Okay, Cl is a nonmetal. Nonmetals tend to gain electrons. They don't always. Sometimes they don't do that. Sometimes they don't become ions. But when they do become ions, they tend to gain electrons, and they form negatively charged ions, which we call anions. Okay. Sodium forms a +1 ion. So we never put the 1, we just put a plus. Cl forms a -1 ion. Okay, so now let's look on the periodic table and find chlorine, and sodium. Here's sodium on the left. Okay, so let's talk about the ion that it forms. So sodium loses 1 electron. Okay, and so it forms a +1 ion. Now, when it loses this electron, what happens to the number of electrons? So sodium itself has 11 electrons. When it loses an electron, it has 10 electrons. So 10 electrons, that's the number of electrons of the previous noble gas, right? So we're going back. And we find the first noble gas that we see is neon, and it has 10 electrons. So when it loses, did I say, yeah, it loses an electron, it has the same number of electrons as the previous noble gas. Okay. Chlorine, on the other hand, gains an electron. So here's Cl. It gains an electron, and it forms a -1 ion. Chlorine has 17. You know, because I'm recording, I can't, it's stopping me from doing things like erase easily. So I don't know, that's what I have to do to record them. It's kind of annoying, but so Cl has 17 electrons. If it gains one, then it has 18. Now that puts it with the same number of electrons as the next noble gas. So it's like each of these things, the metal on the left side of the periodic table is trying to lose the number of electrons to get to the previous noble gas, but nonmetals on the right are trying to gain electrons so that it has the same number of electrons as the next noble gas. You have a question about that? Yeah, you should say why. And why is in chapter, I believe, chapter 6 or 7. I can't remember which one exactly, but we will get to that. Yes. That's how it makes it. It's just simply attractions of plus and minus charges. The sodium is no more attracted to the Cl on one side than it is to the Cls on all the other sides. They're all ionic bonds. No, they're well, you know, it's their electron clouds, really. There's overlap and stuff like that, but it's not like, it's like that sodium is always positive. I mean, the fact that it's attracted to the Cl doesn't make it any less positive. It's just, you know, it's just attracted to all those negative charges around it. So I would not consider one sodium ion and one chloride ion to be anything but the simplest way of saying sodium chloride, right? That it's really a continuous array of charges, and they're attracted by these attractions of unlike charges. So maybe, I don't know, that's the way I see it. All right, so anyway, it becomes 18 electrons, and that's it's the same number of electrons as the next noble gas. Okay, did it again. This is because I'm recording it. Very sorry. What the heck happened? Why is it doing this? Well, it's still recording. Yeah, that's the problem. Oh, I know, I'm not doing this anymore. Keeps bopping me out of OneNote. I don't know why, but I'm not happy with it. Now I have 2 of them open. Oh, well. Okay. So this is true in general, this business about metals tending to lose electrons to become like the previous noble gas, and non-metals tending to gain electrons to become like the previous noble gas. Okay, all of these issues are because I'm trying to record this class. And maybe I have to stop recording because this is not really working. Okay. All right. I hope they can do this. All right. So this is true in general. Metals tend to lose electrons and become like the previous noble gas in terms of the number of electrons. And nonmetals, I'm going to tend to gain electrons and become like the previous noble gas. Okay. So what does this mean? Okay. Now let's take a look at the periodic table. Okay. So that means that in group 1 of the periodic table, so this group, here's group 1. And we already did sodium. Sodium, remember, it loses 1 electron to become like the previous noble gas. So does potassium. It loses an electron to become like the previous noble gas. So in group 1A, these metals tend to lose 1 electron. What about group 2A? So here's group 2A. These, how many would they have to lose? They'd have to go back 2 to get to the previous noble gas. They lose 2 electrons to become like the previous noble gas. Okay. And over here, we have some metals down here. Okay, and this is group 3A. Or if you do the other numbering system, it's 13. These tend to lose 3 electrons to become like the previous noble gas. So you can easily remember this because the number of electrons that they lose is equal to the group number if you use the AB group numbers, okay? On the other hand, for these groups here, 5, 6, and 7A, these are nonmetals. In group 5, how many electrons do you have to gain to become like the noble gas that comes after. No, you go from 5, you'd have to gain 1. So nitrogen, for example, if it gained 1, it'd be like oxygen. If it gained 2, it'd be like fluorine. If it gains 3, it's like the noble gas. So you'd have to add 3 to group 5A. So 5A, we have nitrogen, P. All right, then it's metalloid. So these guys would gain 3 electrons to become like the noble gas. In group 6, it would be gaining 2 electrons. So this, sorry? What do you mean? So, yeah, we're going to show you I'll show you very soon. Oxygen will have to gain 2. Sulfur would gain 2. Okay. Gaining would be going like for oxygen, oxygen would go from 8 to 9 to 10, it would gain 2, right? It would go 8 to 9, 9 to 10. See what I'm saying? It would gain what it needs to get to the noble gases. Bromine would gain 1. So in group 7, it would gain 1. So depending on how close it is to the noble gases, that determines how many it would gain for these nonmetals. So the O group, that's all the ones under O, they would gain 2 electrons. In group 7, that's the halogens, that's fluorine, chlorine, etc. These would gain 1 electron to be like the nearest noble gas. To be like the next, I should say, noble gas. Does that make sense? So I haven't said anything about the sunken living room in the middle of the periodic table. But for the metals here in groups 1A, 2A, and 3A, by the way, hydrogen is a non-metal, but it does form a +1 ion. Yes, question way in the back. All right, group 4A, I didn't say anything because they really, at least carbon doesn't really gain or lose electrons. So I just didn't include it, yeah. Okay, so for these, so what I did here in this chart was I kind of scrunched together all the A groups. So notice we have, lithium, soda. This is the first group of the periodic table, the second group. But then for the third group, remember, it's really aluminum, that these metals, these guys down here that are metals. So I just kind of took out the transition elements and scrunched them together. So you could see that the first group, +1, +2, and then you have here on top, -3, -2, -1, okay? All right. It didn't put charges on some of them because they don't really form ions most of the time. Okay, like carbon doesn't really form ions. But when they do form ions, remember, I don't have the halogens here. 8A would be here. This would have to gain 1. This guy would have to gain 2, etc. All right, so let's see if we can work with this. So the main group elements yield ions that are pretty predictable in terms of what their charges would be. So it's pretty straightforward to predict the ions from these main group, that means the A groups, elements. So what about the transition metals in that group in the middle? So these are the B groups, these are the transition elements, and I like this periodic table because it numbers it both ways. You see that? It's got the 1 through 18, and it also has the 1A, 2A, and 3A, 1A, 2A, and then 3B to whatever, and then 3A on the right. So if I give you a periodic table, I'm going to try to give you this one that has both numberings on it. Okay, so we're talking about the B groups now, and it's not easy to predict what the charges are going to be for these transition elements. So it's more difficult to predict the charges for these B group elements. And one reason is that many elements here can have more than one ion with different charges. Many elements have more than one possible charge on their ions. We know these are going to be positive ions, right? Because they are metals, but we don't know what the charge is going to be. But the good news, there is some good news here. And that is that the charge, you can get the charge from the name. The good news is the name tells you the charge in many cases. Okay, so let me show you what I mean by that. So here I have a chart, and of the transition metal ion charges. Here we go. I think I'm going to add these two. All right. So so here we have chromium. Chromium can be +2 or it can be +3. The way you know which one is being talked about is that chromium with a +2 charge is called chromium 2. So this matches the charge. Okay, this guy is called chromium 3. It matches the charge. It uses Roman numbers, but generally it doesn't go above 2 or 3. So it's pretty easy to put it in Roman numbers. Manganese +2. All right, so then we have like iron can be +2 or +3. The +2 one we call iron 2. The +3 one we call iron 3. Again, it matches the number. Okay, and there are other examples of this as well. So while they're not so predictable, the name essentially gives it away. And I tend to give you these charts anyway on any quiz or exam. So there's not as much memory involved as we used to teach in this class. Okay, so ionic compounds form from positive and negative charged ions together. Okay, but the ionic compounds themselves, and this kind of speaks back to your question, Juliana, ionic compounds themselves are neutral because the charges cancel, okay? And you have to have a neutral overall compound. You can't have a charged compound, all right? So what has to happen in ionic compounds is the number of positive and negative charges has to be the same. So however many positive charges, that's how many negative charges it has to have, and vice versa. The sum has to be 0. So let me show you, like with sodium chloride, for example. God, I can't erase anymore. I've been trying to erase this thing for like 5 minutes. Okay, so let's do an example of sodium chloride. In 1 formula unit of sodium chloride, 1 formula unit has 1 sodium plus and 1 Cl minus. Okay, so it has a +1 charge from that, a -1 from that, and its sum is equal to 0. Okay, so we say that the compound NaCl is neutral because the charges cancel. Okay, so let me talk about MgCl2. Okay, so MgCl2, 1 formula unit, has 1 magnesium. Now, what is the charge on magnesium? Take a look on your periodic table. Where is Mg in the periodic table? It's in 2A, so what is its charge going to be on the ion? Say it, +2. And chloride is Cl minus, right? It's in the last column, right? It's in column 7A. So in order to get the number of electrons of the next noble gas, it would have to gain 1. So you just count 1 over from group 7 to the final group. Are you with me on this? All right. So it's got 1 negative charge, right? It's in group 7. It's in group 7A. It's a column in this. Here's Cl. The next one, 8A, is in noble gases. Okay. So it only has to go 1 over to get to the end of the periodic table. This is argon, which I can't seem to write because it just won't write. Okay. It just have just 1. Gains just 1 electron. Okay. But there's 2 chlorides. Notice there's a 2 here. And the reason there has to be 2 is because 2 Cl minuses gives a charge of -2. 1 Mg plus gives a charge of +2. And they sum to 0, neutral. Okay. All right. So I'm going to show you some pictures next. If you look at the next page, there are some pictures of different ionic compounds. And you'll notice NaCl, which I've already showed you. And then there's CaF2. All right, here we go. So if you look at these different structures, you can see that there's just a continuous array of particles, okay? And you could tell by the different colors, the different ions that they come from. You can't maybe tell which is which, but because you don't know enough about it, but there is no cluster that you would say, oh, that's a molecule. Nah. If you look at these compounds, these are molecular. And you can see individual molecules here. You could see this is a CO2. Here's another cluster. And then you could have some very big molecules, but you could see that these are grouped together. They are not a continuous array like the ones on top, okay? Like these. This is just a continuous array of charged particles. Okay. All right, so I'm going to talk a little bit about naming ionic compounds, because this is something that we do. And so forget it. I'm not recording this anymore. I'm hoping that's what it is.